Hello. This video is about momentum and its conservation in two dimensions. Remember that momentum is a vector quantity, which means it has both a magnitude and a direction. The direction is going to be really important when we're moving in two dimensions. Also recall that something that's moving in two directions has both an x and y, or horizontal and vertical, component and velocity. So back when we were dealing with projectiles and things moving in two directions, we would typically resolve the velocity into a horizontal and vertical component. Well, the same is true of momentum. So we're going to have both an x and y component of momentum as well. So as a simple example, suppose we have this object, which is 4 kilograms in mass, but it's moving at 20 meters per second above the horizontal by 30 degrees. We can construct a vector diagram and break that velocity up into two directions, a Vx and a Vy. And then use a little bit of trigonometry to figure out what the y component is, using the sine, and the x component using the cosine. The x and y momentum would simply be the mass multiplied by the component of velocity. So the y component of momentum would be 4 times 10, which is 40. The x component would be 4 times 17, which is 69.2. And so we can consider this object to have both a x and y component of momentum. Just like momentum in one direction, momentum is conserved in both directions if we have a closed system. So if we know that a system has no external forces, both of those momentums are going to be conserved for the system. So, for example, suppose we had a glancing collision. A good example of that is if you've ever played pool or billiards, depending on how fancy you are, and you shot a ball at another ball, and afterwards they go off at an angle to each other. This occurs quite often in that game. Let's suppose we have a situation like this. We have a red ball whose momentum going forward is 20 kilogram meters per second. It collides with a blue ball. After the collision, the red ball continues moving forward and has 12 kilogram meters per second momentum going forward, but it also now has 5 kilogram meters per second momentum going upwards. Those two numbers are in no way related to the 20. So where does the extra momentum go to or come from? Well, that would be from the blue ball. So let's see if we can figure out what the momentums are for the blue ball. First thing we're going to do is figure out how much momentum we have in our system. In the x direction, the momentum of the red object is 20 kilogram meters per second, and the blue one's not moving, so it's got 0. So the system's momentum in the x direction is 20 kilogram meters per second. In the y direction, they're both at rest. There's no vertical movement, so the y momentum would be 0. Now, if it weren't for the fact that the collision was glancing, we probably wouldn't care about that. But because we end up with an object going up and an object going down, it's important to realize that vertical momentum is 0. Now the momentum of my system is going to be conserved in the x direction, so afterwards my momentum will be 20 kilogram meters per second, and the vertical momentum will still be 0. We know that because momentum is being conserved. There's no outside forces acting on this thing. So kind of redrawing this to give myself more room to work, we can now figure out what the momentum of the blue object is in each direction. I know that the momentum of the system will be equal to the momentum of the red object plus the momentum of the blue object, all of those in the x direction. And so solving for px prime, I get 8 kilogram meters per second. That means that the forward momentum of the blue object is 8. Notice that the 8 plus 12 adds back up to give you 20. Do the same thing in the y direction. 0, which is the system's momentum in the y direction, is equal to 5 kilogram meters per second plus the y momentum of the blue object. And so solving for the momentum of the blue object, you would get -5. Negative because it's going down. So in this collision, in order for there to be any upwards motion, we also have to have the same amount of corresponding downward motion. If you had the masses of these two objects, you can then take those momentum and divide by the mass to figure out what the velocity is in each direction. Let's look at a second example. Suppose we have two cars collide and stick together, and rather than try to describe it, we're just going to draw a picture. I've got one car of mass 50 kilograms going at 8 meters per second to the right, and a second car of mass 50 kilograms moving upward at 6 meters per second. So maybe this is a situation like where two cars that are traveling, one traveling north, the other traveling east, happen to meet at an intersection because they run a stop sign or something like that. So they're going to stick together, and what we want to do is figure out how fast they're going after the collision. So this is still an inelastic collision. They're sticking together. The only difference between this and things we've done in the past is we have to worry about two directions of motion, not just one. Still going to start out the same way. We're going to figure out how much momentum the system has. So the red car has an x momentum of 400 kilogram meters per second and a y momentum of 0. The blue car has an x momentum of 0 and a y momentum of 300 kilogram meters per second. So finding the momentum of my system, I'm just going to add those numbers up. The x momentum will be 400. The y momentum would be 300. So it's 400 going to the right, 300 going up. Momentum is conserved, as it is in all collisions, and so the x and y momentum over on the other side will be the same. I'm just going to write those over there. That means that my two cars will have 400 kilogram meters per second of forward momentum, 300 kilogram meters per second of upwards momentum. So now that we know what the momentum going in each direction is, we can do a vector diagram and figure out the net momentum, like the resultant momentum, and use that to figure out their velocity. So kind of redrawing this again so that I have a little bit more room to work with, we have a vector diagram where we have 400 kilogram meters per second momentum going to the right, 300 kilogram meters per second going upwards, and so the resultant momentum would look like that. Since we're being asked to find a vector, we would probably want to also figure out what that angle is. And so this is just a vector diagram, just like we've done before. We can use Pythagorean's theorem to figure out the size of the resultant, or just recognize it's a 3, 4, 5 right triangle, which is always a nice time saver. Likewise, we can find the angle using the inverse tangent. Take the inverse tangent of 300 over 400, and you'd get the familiar 37-degree angle. Since I want to know the velocity, I'm going to take that momentum, divide by the mass of the system, so be sure to add the two objects' mass together, and just divide, so we would get a new velocity of 5 meters per second, and then don't forget about the direction. It's going at a 37-degree angle above horizontal or above the right. So our method of attack here is the same as it's been with momentum conservation. Figure out the momentum of the system first. Here we just have to realize that there's two momentums, one going forward, one going up, and that we can use vector diagrams to figure out what the resultant is. It just adds another level of complexity to these kinds of situations. So here are the keys. Number one, remember that momentum is conserved in both directions. It's an important fact to need to be able to use. And then we need to be able to use all of our vector operations. And that's the end. Of course, we'll do a lot more practice in class, so make sure that you bring both your thinking brain and your graphing or scientific calculator to class next time.